All right, so today is the 19th of May, 2021, and this is lecture 20. Okay, so let's see where we are. Last time we did this example, um, considered a single degree of freedom undamped system subjected to this ramp loading, okay? And we use the Duhamel integral to find the maximum response of the system. And we noticed that in order to find the maximum displacement, you have two functions for u. One, when the force is acting, in other words, time is before um, forcing function has reached T naught, and here, and the maximum displacement happened to be during the free vibration part, okay? You recall that it was quite extensive to, quite an extensive process to do the integration and find those responses. So what I'm going to show you today through solving another example, which is actually more involved, an alternative way to find the solution to Duhamel integral problem. So let's begin. This is the problem that we want to do. We have a water tower with the weight of the uh, tower given at 100,000 pound. The stiffness of the column is given as 3 times 10 to the 5 pound per inch. And this water tower is subjected to a blast loading, okay, that has the duration of T naught, and the total time is 0.03. So in other words, half of it is 0.015. And the magnitude of the forcing function or the magnitude of this uh, maximum value of the blast load is 100,000 pounds, okay? And we want to find maximum displacement that this water tower experiences. Obviously, you would ask the same question when this forcing acts is of course, very short duration. Would the maximum occur here, here, or here? Okay. Blast loadings are always a major concern. Imagine this is a water tower somewhere, and a bomb is dropped somewhere nearby. This is the blast loading it causes, and we want to know if the water tower would fail or not. Okay. So first, let's um, calculate all the basic information that we need. Mass is given by, this is the weight, so that would be 100,000 divided by 32.2 G, and 12 to convert that to 258 0.8 slugs, which is pound second squared per inch. So that's mass. Okay. K is given as 3 times 10 to the 5 pound per inch. Therefore, natural frequency, which is K over M, will be 34.1 radians per second. Okay. And natural period is 2 pi over omega n, and that would be roughly 0.1845. And the reason I found this is to show you that the blast loading that is acting on the system, its duration is much, much less than the natural period. This is important later on when we talk about response spectrum, because the maximum response is always for general loadings like this is expressed in terms of the relative value of the duration of the loading to the natural period of the system. But for the time being, we just want to find the maximum value of the response of this water tower under the action of this loading. So what was the procedure? Step one, we would formulate the forcing function. In this case, we have three different regions. For the region tau is greater than 0, less than t naught over 2, forcing function is 2f naught uh, tau divided by t naught, so 2f naught tau divided by t naught. When tau is greater than t naught, less than, or when tau, in other words, if let me label these, if I call this region 1, region 2, and region 3, this is for, or maybe since I'm calling these step 1 and 2, I call this A, B, and C. So this is A, this is B, and here forcing function is 2f naught times 1 minus tau over t naught for this function. And for region C, where tau is greater than t naught, forcing function is 0. So we need to evaluate this function, the Duhamel integral, okay, for each of those regions, and then find out in which one of those regions uh, the this would be maximum. Okay, so let's evaluate this for each of these um, three cases. Okay, now first let me write down the first one. So for region A, when tau is greater than 0, less than t naught over 2, okay, you have the forcing function is given by uh, 2 is given by 2 f naught tau over t naught. So what you need to do is what? You write u is 1 over m omega n 0 to t of 2 f naught tau over t naught sine omega n t minus t naught d tau. And this simplifies to 2 f naught over m n. This is constant, so comes out of the integral. So the integral that you need to perform is this, tau sine omega n t minus tau d tau. Okay. And remember, this is the same integral we had in the first problem we did. So I'm just going to take advantage of that answer and write it down. So this will be tau over omega n cosine omega n t minus tau, okay, going from 0 to t minus 1 over omega n integral from 0 to t cosine omega n t minus tau d tau. So if you remember, we used integration by parts to come up with that. But let me pause here because we have two more integrals to do. You remember how long it took us to just set up, to find this integral by using integration by parts. So you can imagine that as the function becomes more complicated, performing this integration gets to become even a more difficult job, right? So for that reason, and for the time being that we are talking about the closed form solution for Duhamel integral, I have included a table, okay, in the notes that I have posted on Canvas. If you look at week 8 module, you will see the notes called lecture 21 plus 22. If you go there, you'll see this. This is the set of notes that you find, which has this problem. Right after that problem, which I'm going to go over that in details, okay, you will see a table with 20 cases tabulated, okay, 20 cases tabulated for Duhamel integral solution for systems that are subjected to these functions, these loading functions. So I have these, go to the next page, you see quite a few more cases, and there are 20 cases that I've tabulated. So I find that the function that I have in this problem is this one, and these are the solutions given for each case. Forcing here, this forcing, and this. So I'm not going to do the integration. I will suffice by using this table. And that's what I encourage you to do if you're given a Duhamel integral problem, which I believe you have for homework number 4, which is the last set of homework. So that's what I'm going to use. So let's do that.
Professor,
Yes,
for the exam or for the final exam, if we have one, is it okay if we use that table as well?
absolutely. I don't
Okay.
expect you, because you can imagine for this problem is a good example. You have two different functions, and in fact, the second one is even more complicated than the first one. And if you wanted to do integration by parts, you're talking about at least 6 or 7 pages of integration or solving that integral. And I'm not that crazy to expect you to do that. In fact, after I'm done with this problem, I will even tell you, okay, why in the world you're using Duhamel integral and if that is a feasible thing to do. Okay. So I'm going to use this. And if I look it up, you see that for case A, the answer is given. U is 2F naught over K T naught times T minus 1 over omega n sine omega n T. So this is a solution for that part. Okay. How did I end up doing that? As I said, by performing obviously these integrations, but I'm going to use that. Okay. All right. So this is the response for this system in this region. That is, when the forcing function goes from 0 to t naught over 2, okay, and described by the function that was given, which is this function, okay? So let's go to region B, which is this one, okay? That is so this is for tau greater than 0, less than t naught over 2. For tau greater than t naught over 2, less than, less than t0, which is this region, you need to set up again the Duhamel integral. So Duhamel integral would consist of two parts, from here to here and here to here. So you have 1 over m omega n times the integral from 0 to t naught over 2 plus the integral from t naught over 2 to t, okay? Okay? And those functions would be this. You have 1 over m omega n times integral from 0 to t naught over 2. This was the function we had, okay? T naught sine omega n t minus t naught d tau plus, so that's this one. For this one would be integral from t naught over 2 to t of 2f naught, okay, times 1 minus tau over t naught sine omega n t minus t naught d tau. So that's this integral. As I said, though, I'm not going to go through these integrations. You can imagine here, look at here. You have one integration by part here, and you have another one here. Actually, two of them here. So it's messy if you want to do that. So fortunately, that table is given. So I'm just going to write it down. From that table, this is the solution. Okay, T naught times T naught minus T plus 1 over omega n times 2 sine omega n T minus T naught over 2 minus sine omega n t. So this is the solution for this region that I found from that table. So there's one more region, okay? And that's after the forcing function has stopped, which I call that region C. Again, for region C, okay, if you want to use the Duhamel integral, would be 1 over m omega n, performing the integration for this region plus t naught over 2 to t naught plus integral from t naught, t0, t naught to t. So you have to perform all these integrals. This one obviously is 0 because there is no forcing function, but you need to evaluate these integrals. But again, I'm not going to do that. I'll just write down the answer from that table, which is this, k t naught.
I have a question.
Sure.
I guess I'm just looking at B and C. would they not be the same answer? Because you
No,
just don't have that third integral.
no, you see, you mean these two should be the same? Is that what you're saying?
No. Between B and C.
Oh, between B and C, good point, point. See, the difference between B and C would be that here you're evaluating the response when this forcing function has not reached this specific value anywhere here. So as a function of t, looks like this. For here on, what happens, you have a free vibration, and this free vibration is caused by the initial velocity and initial displacement at this point. In other words, you go to here, right? Set
Yeah.
t is equal to t naught. That would be u at this point. Take the derivative of it, put t is equal to t naught, would be the displacement at this point. Then you use those initial conditions, substitute in the free vibration equation, and this is what you end up with, which would be, which looks
Okay.
like,
Thank you.
oh, thank you, would be this, sine 2 sine omega n t minus t naught over 2 minus sine omega n t minus sine omega n t minus t naught. So that's what this function would look like for the free vibration part. Okay, so this is for t greater than t naught or free vibration. Okay, so let me rewrite these, summarize what we have done. The summary is this. Okay, we are asked to find the maximum response, okay, for the response of this water tower under the action of this load, and we found the equations for the response in each of these regions as follows. I'm just going to rewrite them because we will need them. So for this region was 2f naught over k t naught times t minus 1 over omega n sine omega n t. For this region was u was 2f naught over k t naught times t naught minus t plus 1 over omega n times 2 sine omega n t minus t naught over 2 minus sine omega n t. Sorry for the little bit of a messiness. And here u is 2f naught over kt naught omega n times 2 sine omega n times t minus t naught over 2 minus sine omega nt minus sine omega n t minus t naught. So the question is, which one of these will give me the maximum displacement? Because we want the maximum displacement of caused by this forcing function. We want to know what is that maximum value. Would the maximum value occur here, here, or here? In order to find that out, what do you need to do? You will need to take the derivative of these in each region, set that derivative equal to 0, that will give you the time at which supposedly that function has reached maximum. Substitute that into that equation, find the corresponding maximum, do that for each of these, and then compare and see which one is the absolute maximum, right? So let's start with that. So I will take the derivative of each for each case, because we need that. Set that equal to 0 to find the maximum in that region. So derivative of this function, I call it a prime, du dt, take the derivative, would be 2f naught over kt naught times 1 minus cosine omega n t. This is when this is greater than 0, less than t naught over 2. For the second region, derivative, if you take the derivative of this function, you get -1 plus 2 cosine omega n t minus t naught over 2 minus cosine omega n t. So this is for t greater than t naught over 2 and less than t naught. And for the third region, du dt would be 2f naught over kt naught times 2 cosine omega n t minus t naught over 2 minus cosine omega n t minus cosine omega n t minus t naught. So this is when t is greater than t naught.
Professor, for case B prime, what you have there, are we missing the coefficients out front, 2FO, K?
Oh, yes, I'm glad that you said that. Sorry, I thought I was getting smart, so doing it quicker. So let's, yes, you have also 2f naught over k t naught. Thanks for the observation. And that's what this one. So now, before I go and set these.
Professor,
Yes.
are you also missing the omega n on C prime?
No, for actually, when you do that here, I didn't go through the derivation. When you take the derivative here, you will have 1 over omega n. That 1 over omega n comes out, becomes omega n squared, and so on. So it simplifies to that. I didn't go through that.
All right, thank you.
Sure. So before I proceed any further, let's substitute for those numerical values that were given. Omega n is 34.1 radians per second. T naught is 0.03 seconds. And as you will see, when I do the expansion of these to set them equal to 0, I need to expand these functions. So for instance, cosine omega n t minus t naught half would be cosine, sine, cosine of this, sine of that, minus cosine of this, sine of that. So you end up with omega n t naught over 2. So I need that. So I have also evaluated that. That would be 0.5108. This is 0.03, this is that. So I have these quantities. Okay, so now let's see what we're going to do. We want to find out where these three functions would be maximum. Okay? That means I want to find out where these are going to become 0, right? So let's start with this guy. In other words, while we are in this region. You see that as t goes from 0 all the way to t naught over 2, which is 0.015 increases. If you look at this function, this derivative, this, for any value of t, between 0 and 0.05, this is always smaller than 1. What does that mean? That means anywhere from here to here, this function has a positive slope all the way from here to here. That means that slope will never reach 0. So for a prime, du dt will remain positive. What does that mean? That means in this region, function had looked like something like this. The slope, which is represented by du dt, has stayed positive, meaning that the displacement will never reach a maximum value in this region. Do you follow me? If you have any question, please let me know. I wanted to find the maximum value. I took the derivative. I need to find a time at which these derivatives go to 0. So I go to the first derivative, and this derivative in this region will never become 0. In fact, for the values given, it will always be positive all the way to here when time has reached t naught over 2. So we conclude that U max cannot be reached, okay, in the region when t is greater than 1 and less than t over 2. So let's go to the next one. Let's go to this one, B prime. Again, look at du dt. Now we're going from 0, t is 0 over 2, all the way to t naught. So in other words, we are going from 0.015 to all the way 0.03, okay? And in this function, or in this relationship, okay, if you consider that -1 plus 2 cosine omega n t minus t naught over 2 minus cosine omega n t, okay? If you substitute for any value in this range, you see that this will always be a positive value. You can try it. Just use, for instance, t is 0.02, which this becomes a positive value. So this is of course, that's a small number, so it's almost equal to 1.98 minus 1 minus 1, 0.98. And this is a very, very small value. So this remains a positive value. What does that mean? That means that this function, okay, which was going like this, from here to here, continues to have a positive slope even up to here, when t has reached a value of t naught. So what do we conclude then? Okay. In fact, let me show you. Let me do some number here. For instance, I'm going to substitute for t equal to t naught, which is the maximum value of t here. If you do that, you get 2f naught over k times 0.03 times -1 plus 2 cosine 0.03 minus 0.015 times omega n would become 0.5108 minus cosine of omega n 34.1 times 0.03 would be cosine of 1.0216. This becomes 2f naught divided by k times 0.2227 divided by 0.03, which is a positive value. So we conclude then, if a maximum response is reached, has to be at some point after the force has been terminated during the free vibration region, because up to here, the slopes remain positive. The function cannot reach a plateau of, derivative going to 0 or the function becoming maximum. So we conclude then that U max will occur. So conclusion is that U max, okay, will be reached when t is greater than t naught, or in other words, when u is given by this function, k t naught omega n 2 sine omega n t minus t naught over 2 minus sine omega n t minus sine omega n t minus t naught. So the maximum value can only be reached when the response is given by this function. So how do you find the maximum value? Okay. First of all, I want to find the maximum value of this, right? One option is use this equation for C, for du, for the derivative, set this equal to 0 and find t, substitute that into that equation, right? You can imagine how difficult that would be. I have an easier way of doing it. How? Let's look at this. First of all, let me simplify what we have here by replacing these with using trig identities. So I have this term I call alpha, this term I call beta, and expand these. So this bracket would be expanded to this, 2 sine omega n t cosine omega n t naught over 2 minus cosine omega n t sine omega n t naught over 2. This is alpha using trig identity. Sine of alpha minus beta is sine alpha cosine beta minus cosine beta sine alpha minus sine omega nt, okay? And same thing here. If you expand, that becomes minus sine omega n t, okay, cosine omega n t naught plus cosine omega n t sine omega n t naught. So this is beta, okay? So now, if you substitute for T naught, omega n, and simplify this, rearrange all the terms and do the algebra, you see that this will become 0.2227 sine omega n t minus 0.1248 cosine omega nt. Okay? But remember, we've done this many, many times. This is a1 sine of a function, a2 cosine of a function. This can be written, in other words, this is like a1 sine omega nt plus a2 cosine omega nt. This can be written as a1 plus a2 square root of that times sine of omega nt plus theta. You remember that, right? Because you can write that as multiplied by this, divided by that. So this is the alternative form of that, right? Where theta is obviously is the arctangent of a2 over a1. So u becomes, new, if you substitute in here, u simply becomes 2 f naught, right? K t naught omega n times square root of a1 squared plus a2 squared sine omega n t plus tau, where a1 is 0.2227, a2 is that 0.1248, okay? F naught is 100,000. K, it was given as 3 times 10 to the 5 pound per inch, okay? Omega n was 34.1 radians per second. T naught was 0.03. So you substitute all of these values into that equation, you get what? This is the amplitude of this function. So this is your u max, right? This is the maximum value that this sinusoidal function will take. So u max will be simply 2 times that 100,000 divided by 3 times 10 to the 5 times 0.03 times 34.1 times 0.2227 squared plus 0.1248 squared. If you evaluate this, u max comes out to be 0.1167 inches. It is interesting that if you find the displacement due to just a static load, that is F0 over K, that would be 0.3 inches. So the dynamic load which is this represented by this blast of a short duration, causes less displacement than the static load, okay? So that's, that's why for blast loading, okay, even conservatively, you take dynamic load factor of 2, which you've been using in Shakely. But let me say this. The reason I did this problem was to show you, in fact, how extensive and cumbersome in a way it is to to find response of a function using Duhamel integral, which is a general approach under general loading. Okay, I have a few other examples that in that handout, which I refer to, I have done those. For instance, for a function which is a one cycle, a half cycle, I have asked you to find the dynamic load factor for those. I have also solved this problem. I have solved, and these are using extensive Duhamel integral integrations, but I have done those and also this problem, okay, to just show you how you can find the maximum response using a Duhamel integral. But in reality, obviously, when you have a function, even if it is undamped, okay, under the action of a general load, you can imagine using Duhamel integral is not easy. So the question is, how do you find the response under general loading? And my answer is you use numerical integration. And I will discuss that next time. So I'm going to stop here. And if you have any questions, please let me know. Otherwise, I'll see you during my office hours.